So we proved the Radon-Nikodym theorem. So XS measurable space, mu nu finite measures, nu absolutely continuous with respect to mu. Then there exists F non-negative integrable with respect to mu, such that for every E in S, nu E equal to integral over E F d mu, and F unique up to equality almost everywhere with respect to mu. So if you have some other function g, then f and g are equal almost everywhere as far as mu is concerned. So now we want to extend this to the general cases. So let us assume that mu nu sigma finite then you have x equals union en, n equals 1 to infinity, equals union fm, m equals 1 to infinity, where mu of en is all finite and nu of em is finite for all n, for all m. Okay, so then x can be written as union n equals 1 to infinity, union m equals 1 to infinity, en intersection fm. Okay, so there exists f and m on en intersection fm, non-negative integrable with respect to mu, such that nu of e equals integral over e f and m d mu for all e contained in en intersection fm. Okay, so now from this, so implies, so set f equals f equals f and m on en intersection fm. Okay, then for all e in S, we have nu e equals integral over f over the d mu. Check. Okay, and this f need not be integrable now, and that's because nu is no longer a finite measure. If it's finite measure, f has to be integrable, otherwise it need not be integrable. Okay, so then next is, so if mu and nu are sigma finite measures, we still have the Radon-Nikodym theorem holding true. Okay, so now assume that nu is sigma finite signed measure. Then you can write nu equals nu plus minus nu minus, and these two are sigma finite measures, so nu plus nu minus are also absolutely continuous with respect to mu, and therefore we have for every e in S, you have nu plus of e, nu plus minus of e equals integral f plus minus d mu over e. Okay, so now you take f equals f sub plus minus f minus. This is not the positive and negative parts, but simply the difference of these two functions which we have here. And then you have that nu e equals integral over e f d mu for every e in S. Again, check. Again, these are all very trivial checkings which you can do. So finally, let mu also be sigma finite signed measure. Then let X equals A union B be a Hahn decomposition. So if E is contained in A, then mod mu of E is equal to mu plus of E, and if E is contained in B, then mod mu of E equals mu minus of E. That's obvious, okay, because the E intersection A, E intersection B is empty in the first case, and therefore mod mu minus of E is 0. So mod mu of E is mu plus of E, and this is mod mu of E equals mu minus of E. Okay, so this implies on A, mu plus nu is absolutely continuous with respect to mu plus, and on B, nu is absolutely continuous with respect to mu minus because of this. Okay, so then for every E in S, E contained in A, you have that nu E equals integral over E of Fa d mu. And similarly for every E in S, E contained in B, you have nu E equals integral over E Fb d mu because of the diagram whatever went before. Okay, so now if E belongs to S, then you have nu E equals nu of E intersection A plus nu of E intersection B. Okay, and that is equal to integral E intersection A Fa d mu plus integral E intersection B Fb d mu minus. And that is equal to integral over E Fa chi A minus Fb chi B d mu. Again, check this once more, very trivial checking to be do. So every time we have the thing, and so finally we have the theorem Radon-Nikodym in its full generality. So XS measurable space, mu nu sigma finite signed measures, and nu absolutely continuous with respect to mu. Then there exists a measurable function f such that nu E equals integral f d mu over E for all E in S. Okay, so this question of integrability doesn't come now because you do not have finiteness of the measures. Okay, so now definition. XS measurable space, mu nu sigma finite signed measures, and nu absolutely continuous with respect to mu. So let f be such that nu E equals integral f d mu over E for every E in S. Then f is called the Radon-Nikodym derivative of nu with respect to mu. And symbolically, we write df equals d nu by d mu equal to f. Okay, now why this notation? So let us recall that if you had mu nu measures and nu e equal to integral f d mu over e, then this implies that integral g d mu over x is equal to integral over x f g d mu. Okay, we have seen this thing. We proved it first for characteristic functions, then for simple functions, then for by some theorem, we monotone or dominated, we proved it for the general case. So this exercise which we, or a proposition which we have already seen. So symbolically we can write d nu equals f d mu, and again symbolically we write d nu by d mu is equal to f. These are all symbolic calculations, so don't take them too seriously, otherwise it's just notation, and therefore this is the reason why we call it the Radon-Nikodym derivative. Okay, so then proposition, which is what we have already seen. So this in the general case, so XS measurable space, lambda mu sigma finite measures defined on S, and mu with respect to absolutely continuous. Then new sigma finite measure, nu absolutely continuous with respect to mu. Then nu of course is absolutely continuous with respect to lambda, because if lambda of E is 0, mu of E is 0. If mu of E is 0, then nu equals 0, and d nu by d lambda, you have the usual product rule, d nu by d mu by d lambda, almost everywhere with respect to the measure lambda. So proof. So let f equals d nu by d mu and g equals d mu by d lambda. Okay, then nu e equals integral f d mu over e, but that f d mu over e is equal to integral over e f g d lambda. All these are non-negative because we are having measures, and then we have seen this. Okay, so you have this, so proved earlier. And by the uniqueness with respect to lambda, therefore you have d nu by d lambda is equal to fg almost everywhere with respect to lambda. Okay, and that proves this proposition. Okay, so now we are going to start a new topic called singularity. So this is sort of the antithesis of what is called absolute continuity. When you have absolute continuity of nu with respect to mu, if mu e vanishes, nu e also vanishes. So mu drags nu along with it. But in the singularity, you have mu and nu are sort of independent of each other, and that is made precise in the following definition. Excess measurable space, mu nu measures. So mu, we say nu is singular with respect to mu, and the notation is nu is orthogonal to mu if there exists a E in S such that mu of E is 0 and nu is identically 0 on E complement. Okay, so this is the opposite. So if you have absolute continuity, then mu E equals 0 implies nu E equals 0 and for all subsets. Whereas here nu is 0 where mu is not 0. Okay, and vice versa. So this is the notion of singularity. So example, so let us take M1 Lebesgue measure on R and delta Dirac measure concentrated at the origin 0. Okay. So now if you take E equal to singleton 0 and then you have M1 of E equal to 0 and delta is identically 0 on E complement. Okay, so you have delta is singular with respect to M1. Example again. So XS measurable space, mu is a signed measure. Okay, then mu plus is singular with respect to mu minus and mu minus is singular with respect to mu plus, and the corresponding set which you are looking at will be A or B in the Hahn decomposition according to it. Okay, so proposition, this is called the Lebesgue decomposition. XS measurable space, mu nu sigma finite measures. Then there exist two uniquely defined measures, nu naught and nu 1, such that nu equals nu naught plus nu 1. So I can decompose nu into two measures, nu naught and nu 1, and nu naught will be singular with respect to mu and nu 1 will be absolutely continuous with respect to mu. So every measure can be decomposed into two parts, one which is singular with respect to another given measure and the other one will be absolutely continuous with respect to the same measure. So proof, we have nu trivially is less than mu plus nu. This is obvious, and therefore there exists f non-negative such that nu e equals the integral over e f d mu plus nu for every e in S. So you take A to be equal to set of all x in X such that fx is greater or equal to 1. And let B to be a complement. That means set of all x in X, fx is strictly less than 1. Okay, and f is of course non-negative, we already know. Okay, so nu a is integral over a of f d mu plus nu, okay, and f is greater than or equal to 1 on a, and therefore this is greater than or equal to integral over a d mu plus nu, which is equal to mu a plus nu a. So nu A is greater or equal to mu A plus nu A, and therefore if you cancel, you get that mu of A equal to 0. So define for E in S nu naught of A, nu naught of E, equals nu of E intersection A, and nu 1 of E equals nu of E intersection B, where B is of course A complement. Then that of course obviously implies that nu equals nu naught plus nu 1, and then mu A is 0, and nu naught is identically 0 on B. Because if any subset of B, then its intersection with A is empty, and therefore this is 0. And therefore this, which is A complement. This means that nu naught is singular with respect to mu. So to show nu 1 is absolutely continuous with respect to mu. So let mu E equal to 0. Then nu 1 of E equals integral E intersection B d nu, which is equal to integral F d mu over E intersection B plus integral E intersection B F d nu. But mu E equal to 0, so this term will disappear, and therefore you have that integral E intersection B of 1 minus F d nu equal to 0. But on B, 1 minus F is strictly positive, and therefore this implies that nu of E intersection B equal to 0, that is nu 1 of E equal to 0. So mu E equal to 0 implies nu 1 of E is 0, and therefore you have nu 1 is absolutely continuous with respect to mu. Finally, we have to show that it is uniqueness. So let us take nu equals nu naught plus nu 1, which is also equal to nu naught tilde plus nu 1 tilde. Okay, nu naught, nu 1, nu naught tilde, are singular with respect to mu. Nu naught absolutely continuous with respect to mu. Nu 1 also absolutely continuous with respect to mu. So let A be the set such that mu A equal to 0 and nu naught identically 0 on A complement, and A tilde, mu of A tilde equal to 0, nu naught tilde identically 0 on A tilde complement. So we have just applied the definition so far. Okay. So mu of A union A tilde equal to 0, and A union A tilde complement is A complement intersection A tilde complement, and both nu naught and nu naught tilde vanish on this set. So you set lambda equals nu naught minus nu naught tilde equals nu 1 minus nu 1 tilde minus nu 1. So clearly lambda equals nu1 tilde minus nu1 is absolutely continuous with respect to mu. There is no doubt about that. And so we have and this, since mu of A union A tilde is 0, we have lambda equal to 0 on A union A tilde and all subsets. Because on all subsets mu is a measure, okay, so it's true for all subsets also because of the absolute continuity, not because lambda is a measure, okay. Now on the other hand, we have that nu naught minus nu naught tilde is identically 0 on A union A tilde complement. That is, lambda is identically 0 on this. So lambda vanishes on A union A tilde, lambda vanishes on A union A tilde complement, and this implies that lambda is identically 0. That is, nu naught equals nu naught tilde and nu1 equals nu1 tilde. So the decomposition, Lebesgue decomposition, is uniquely defined here. So this means here we have that lambda is both singular and absolutely continuous with respect to mu. That is what we have had, and that shows that it has to be trivially a zero measure. Okay, so this completes. So we will do some exercises before we conclude this chapter.